language. cuda is a procedural language we can implement using usual create function statement. And it allows to implement raw CUDA code blocks. These are an example. That is what I will introduce later, CUDA function for similarity search. These code block can be executable. This remote desktop is on my development environment in Tokyo. And here is GPU installed PostgreSQL environment. I like to execute a CPU version of a similarity search first. Probably it shall be completed later half of my talk. It is CPU version of similarity search, kernel CPU similarity. So timing on. So let's execute it. And okay, let's go to the presentation. I'm Kaiga Kohei of NEC. Have been a contributor of PostgreSQL over 10 years, and recently I'm focused on pgstrom. That is an extension for GPU acceleration on PostgreSQL workload. That diagram is a brief overview of pgstrom. It is extension. Once we install a pgstrom extension to PostgreSQL, it interacts with PostgreSQL optimizer and executor. Once user send query to PostgreSQL, optimizer asks the pgstrom extension whether this SQL query can be executable on GPU devices. Once the workload like join and scan aggregation executable on GPU devices, pgstrom construct a custom scan path and register its execution path to the optimizer. Optimizer checks the cost value of all possible execution paths, and if GPU execution path is cheapest, it is selected, and next executor calls pgstrom call to execute SQL workload on GPU devices. GPU is an excellent device. It has much more processing core to the CPU, but this processing core has a simple functionality, so we cannot apply any kind of problem to GPU. We have to investigate what kind of problem is suitable or not. One other characteristic is memory band. GPU mount much high performance memory than usual CPUs. So when we make code for GPUs, when we write GPU code, it is recommended to utilize many cores and high memory band. One existing characteristic of pgstrom is auto GPU code generation. Once a query is supplied, it makes GPU code on the fly and compile on demand and run on GPU devices. This process, a series of steps completely transparent. So from the standpoint users, it looks like a normal PostgreSQL, but internal execution engine uses GPU devices. Its performance is excellent. It is a simple micro benchmark when we join the multiple tables. In case when we join the one large table and one small table, normal PostgreSQL returns the query in 40 seconds, but pgstrong returned about 10 seconds. And according to the increase of number of tables, response time will grow rapidly on PostgreSQL case, but in case of pgstrong, the increase of response time is very flat. However, under the development of version 1.0, I get some feedbacks from users. Here is two major concerns for users. One is heavy computing intensive workload. Because R&D people runs advanced analytic algorithm. Usually it is executed external application because of the computing performance of database systems. However, auto-generated GPU code was not answer for the solution because of some reasons. So I made a new feature to stick on this kind of workload. It is today's topic, PL CUDA and matrix array data type. And one other feature is one other request is a heavy I/O workload. That is the case when the total amount of data size is larger than physical RAM. In this case, entire dominance factor is I/O, not the CPU and GPU. Once we had to fetch data from a storage system, it eliminates advantages of calculation stages. So we also add another feature that is SSD to GPU direct DMA. That is not today's topic, so if you're interested in, please ask me privately. So let's move to today's topic, PL CUDA. First of all, I'd like to introduce the background why I had to design a PL CUDA. That is one slide on a conference half years before. At that time, I tried to run advanced algorithm stuff on the PostgreSQL. At that time, we have no procedural language features, so I tried to describe a core of algorithm logic in SQL. In this logic, the core of the algorithm is distance calculation here. It made much acceleration in comparison to bare PostgreSQL. In case of PostgreSQL, its response time grows more rapidly, and pgstrong more faster and faster response time, but its absolute response time is similar to external, specially designed applications. Why? If we are using GPU, why our performance is similar to native CPU applications. Here is some reasons and problems. One problem is difficulty to describe the algorithm stuff, and one other problem is performance. Usually, people don't describe an advanced algorithm stuff in SQL. And majority of known algorithms are assumed procedural language manner, like C, Java, and other stuff, not a SQL puzzle. So if we had, even if we don't need to describe a CUDA logic because of autocode generation from SQL, it is same stuff if we enforce users to describe SQL puzzles. And one other problem is performance. The auto-generated code have to follow the SQL compatibility. It means anytime we access a variable, we have to check a null value. Once we had arithmetic operations, we had to add overflow checks and so on. These all stuff decrease the performance, far from the full capability of GPU devices. So we designed a solution for the problem. It is a PL CUDA and matrix-like array. My presentation slide will be published on SlideShare later, so no need to take a photo every page. Don't worry. PL CUDA is a procedural language for PostgreSQL that allows to describe a CUDA code block within a function definition. Once a CUDA code block is defined, it is put into the GPU kernel by the infrastructure, and this raw code block is executed on GPU device. Because this SQL function is executed inside database, we could use the flexibility of SQL for post processes, like a table join, group by and window function. Once we export data to analyze by external applications, we have to write back the result of analytics into a database again. It is an ignorable disadvantage. And one other supporting stuff is a matrix-like array that allows to move a chunk of data with a high density and suitable for GPUs. I'll introduce it later. First of all, it is an example of CUDA function. CUDA is a programming language for GPU devices like C, and we can add these code block in the definition part of a create function. These code blocks are put into the GPU kernel without any changes. Then, we can add some directive within CUDA code block. For example, PL CUDA sanity check directive can specify an external function to check the function argument, whether it is valid or not. And as I introduced, the CUDA code block is moved into the GPU kernel as is. This GPU kernel template supports input and output of an argument and a result set from the SQL world and to the SQL world. And another supporting function can specify the amount of working buffer to run this PL CUDA function. Once this function returns the required amount of working buffer, infrastructure acquires a working buffer on device memory. Then it invokes a GPU kernel with required argument. In case of automatically generated GPU code, for example, this simple multiplex operation needs null checks and overflow checks, and due to our design, it has to be represented as a function call. But once we describe the logic in raw CUDA code, we cannot omit all these unreasonable stuff. So we can prove out maximum capability of GPU devices. And one other point we should consider for GPU acceleration is the date format. PostgreSQL usually uses a raw date format. A record contains multiple columns, and the location of column is unpredictable. So if we try to fetch column B and column E, we have to work on the record from the head. It takes multiple times memory accesses. On the other hand, if we have a data set with a columnar format, all we have to move into the GPU device is a column that is referenced. So it allows to reduce the transfer cost. And on the memory reference stage, the location of the data items is predictable. Individual GPU core knows the location of the target data with head of the array pointer and its own thread ID. This is one advantage of columnar storage. And one other point to be considered for data format is bandwidth and density of the memory bus on GPU. Most of NVIDIA's GPU device has 32-byte windows of memory transaction. In case of low format, the data to be referenced scattered around the device memory. And once we try to fetch 32-byte blocks, small amount of portion buried we like to fetch. So in this case, most of memory band are junk. On the other hand, in case when variable items are located closely and multiple processing core accesses and continuous area, we can utilize entire memory bandwidth of 100%. It is the most efficient access pattern for GPU memories. So how to, I think how to implement it on PostgreSQL. Unuseful facility I found is an array data type. Since array data type allows to contains multi-dimensional and continuous data. If we add constraint of array type data, only fixed length variable and only not null or not null array, we can consider two-dimensional array data type is like as a matrix. And for example, if we have 4 column and n rows arrays, its internal data format is as is described in this diagram. On top of array, the data items of first column is put. Then second column of the item of second column are located next to the first column. So it looks like a columnar format suitable for GPU devices. And we add two functions to transform a stream of record into two-dimensional array and revert two-dimensional array into a stream of records, array matrix and matrix and nest. Of course, here is a downside. Due to the restriction of PostgreSQL's variable length data type, it has a 1 GB limitation at this moment. So if we have to handle the data set larger than 1 GB, we have to split into a multiple part. It is a future issue at this moment. And this is an example to call pure cuda function. The deepest level of this query scans tables, and this array matrix function constructs two-dimensional array. This is referenced in a pure cuda function. Its argument is an array matrix. It is moved to a GPU device and run the internal logic of my pure cuda function then write back the result into a PostgreSQL word. After that, matrix NS function revert the result set into a normal bunch of records. And once that set is transformed to a normal record, we can apply a usual SQL function and SQL features. So this is an overview of PL CUDA and matrix array data type. So the later half of this talk, I'd like to introduce the case. I'd like to introduce two cases for PL CUDA usage. First one is similarity search on drug discovery. Let me introduce the background of this workload. Research people in drug discovery area usually try to find chemical compounds that is active to a particular protein. Why particular protein? And these are related to a certain amount of protein. So if we could find out a chemical compound that is active to a particular protein, it may be variable to the target disease. Of course, some chemical compounds are inactive. Some chemical compounds are active but toxic. That is not usable for drugs. What people interested in is an active chemical compound to the target protein. And these information are published in an academic paper day by day. Then what we try to do is similarity search between a set of chemical compound and other set of chemical compound, because some of chemical compounds are known which is active to a particular protein. These are reported on academic papers. Researcher can collect these published information. And on the other hand, here is a catalog. We can collect and test it. Its usual size is up to 10 million chemical compounds. Of course, brute force approach is very unusable because investigation of a chemical compound characteristic is expensive. So we like to pick up a higher probability chemical compounds than others. One approach is to pick up a similar chemical compound with known chemical compounds. So once we try to find a similar chemical compound from the catalog set, we may be able to find out an unknown chemical compound but higher probable to be active to the target protein. It is a problem we try to tackle. So the next problem is how to define the similarity. Here is multiple approach to define a similarity between a set of chemical compounds and one other chemical compound. The approach we adopt is a k-nearest neighbor method. That is we once calculate distance between all the items from the query chemical compound and the target chemical compound, and pick up some item that is nearest to the target chemical compound. And its average, we consider its average is a representative distance. And definition of the similarity is we use is Jaccard index. That is a ratio of bitmap and of the fingerprint and bitmap or of the fingerprint. Fingerprint is a set of characteristics of chemical compounds, like it has a positive ion, it has benzene, and so on. The details, I'm not sure the detail. These are provided by a biological researcher. Anyway, all the things we have to do is calculate the ratio of bitmap count. So entire amount of calculation is not it's not lightweight, because if we have 10 query chemical compound, we have to calculate 10 distance to a particular chemical compound from the database. Then we sort the distance count, then pick up the top three similarity from the result. It is the representative similarity to a particular chemical compound in the database set. Database set contains 10 million records, so we have to iterate 10 million patterns for each. So entire calculation order is like a cross join, entire Q item and entire D items. And we have to make a distance, and we have to sort for each partitions, for each database chemical compound set. Things we implement is not something special. According to the algorithm definition, we implement cuda logic. This algorithm need to make a logical combination set once. It is Q times D. And it is not so small, so we have to map a particular range into SMM. It is a unit of execution on GPU, and each SMM is responsible to calculate distance between two chemical compounds. These are recorded on the GPU memory. Then it sorted according to the similarity value. Once we sort the similarity value, top K item we can pick up top k item, and its average becomes the representative similarity value of the D item. These are part of the implementation. The actual CUDA code is much longer than we can put into one screen. Anyway, this function took k item and one other matrix array for query chemical compound set, and one other array matrix for database chemical compounds. That returns an ID and similarity values. That returns array matrix for ID and similarity value. And invocation is similar to what I introduced just a moment before. Once in the deepest level, we fetch a database set of the chemical compounds from the table. That is preliminarily constructed because database set is very static. And one other subquery is construction of matrix array for query chemical compounds. These two result is supplied as an argument of PL-CUDA function. Then it runs the core of KNN logic, and it returns a set of ID and similarity value. After that, the result matrix is reverted into a usual record set, and we can process using regular SQL features. The performance improvement is dramatically. When, for comparison, I implemented an equivalent logic with a C function. So it is never slow because this logic implemented in C language is executed on a binary level. But GPU version finish the KNN logic 150 times faster than CPU version. On the beginning of the presentation, I try to kick CPU version, but not yet completed. So, I forgot to interrupt check handler on CPU version. Okay, let me check it later. Sorry. Then let me introduce one other use cases. The topics I pick up is data clustering problem. Clustering analysis is a feature to categorize a massive amount of data set into multiple small amount of categories. Usually, people use hierarchy type clustering and hierarchy type clustering. K-means clustering algorithm is a representative and hierarchy clustering logics. Its core algorithm is never complicated. When we had multiple data, initially we put a category randomly. It is the initial state. Then we calculate a centroid according to the initial random clustering. Once we could get a centroid of the items, update the items class according to the distance from the centroid. Once a centroid is updated, we iterate the location. Once we update the cluster of individual items, we update the centroid location again. And it gets converged into a particular category. We finish the K-means clustering logic. Its implementation is also complicated. It's too large to put into a single screen. So anyway, we put multiple functions, and anyway. Several support functions to make a sanity check and put a hint for a working buffer and result buffer size. And things I try to use is dataset from CityPulse project. That is traffic data recorded on Aarhus City on Denmark. That is a collection of dataset for a number of cars and average speed of cars on the observation point. It is 449 observation point here. And what we did is makes a cluster for each observation data and pick up a most frequent category is a representative category on the observation point. Things we did is similar to the previous case. Make an array matrix from the relation, then call the cuda function. And after that, we process the post-core logic operation by SQL. So that is a result of clustering of the observation data. Due to the restriction of Google Map, we cannot put entire lines. So it is a part of categories. But since it looks like blue observation zone looks like bypass or highway. Car runs high speed and many amount of cars. And probably green line looks like a road towards downtown, and road seems to be always crowded, thus car speed is slow. And other red line shows belt way, but I'm not sure the characteristics. Since this clustering logic is described in SQL, we can easily adjust the condition to supply the k-means functions. I try to split the data one for daytime and one other for nighttime. Unfortunately, here is no special difference between two cases. And one other trial is data split between weekday and weekend. Very small difference observed in the road towards downtown. In the weekend, the road to downtown is categorized into the same color with the highway. So we can expect on the weekend, the speed of car to go into downtown is higher than weekdays. Anyway, to create those graphics, things I did is just add where class here. That is quite easy to split dataset into a multiple part. Then, let me wrap up the talks. First of all, what is PL-CUDA? PL-CUDA is a procedural language for PostgreSQL to describe a low CUDA code block. And its advantages is it allows to provide the full capability of GPU devices. And no need to export entire dataset to run advanced analytics logics from the database. It allows to eliminate the extra network traffic to move the dataset. All we need to move the data from database is just result set. It is usually much smaller than a raw dataset. And its future challenge is multiple items. The highest priority is data size larger than 1 gigabyte. It is come from a restriction of variable length format in PostgreSQL. So probably we have to enhance this implementation. And currently, PL-CUDA function is synchronous only. So for more performance, we need to investigate the opportunity for asynchronous execution, but CPU parallel will give a similar feature. So we may not need to implement individually. And time to construct matrix is one headache for us. So on optimization techniques, if the data set is quite static, we can preliminarily build an array matrix on database. So these are resources. The PG-Strong repository is on GitHub, and today's slides are exposed on SlideShare. And here is contact for me. 5 minutes remained. Any questions?
At first, you mentioned you have another direction going is SSD to GPU DMA. Can you tell us more about that?
It's too short to introduce in 5 minutes. So if you interested in, please discuss it later.
So do you have the performance comparison with and without using the matrix?
What's
Do you
it?
have the performance comparison with using the matrix and without using the matrix?
If we don't use matrix, the implementation of a pure CUDA function is completely different. So I didn't measure these two differences, but theoretically, GPU takes much more penalty to access a raw format. So I don't think non-matrix data type will have performance advantages. It's okay for your question? Any other question? Okay. Thank you for your participation.